I am doing pretty good. I'm yeah, we're getting close to the end of network security. I'm excited, a little bit sad, because this is stuff that I really like. Okay, and let's get started. How do we do that?
Professor, when can we expect our next homework assignment? And what might it be on?
On content from the class, undecided as to exactly yet. The goal was to give you a little bit of break after the midterm, so.
Awesome.
Much appreciated.
Yeah, I know it's tough not having spring breaks. You had a spring break of no homework in this class, so sorry, that's the best we could do right now. And the other thing we decided to do is offer extra credit. So if you want to get extra credit on a homework assignment, so basically the way this will count for is basically 10 points of extra credit on one homework assignment. So you don't have to worry about which one because it doesn't matter. They're all, each homework assignment is weighted equally. You'll get that. We don't know how many homeworks you're going to have. It depends on the pace of the course and things like that. So it's something in the syllabus where there'll be 3 to 7. So we've already hit 3. So, I think probably 2 more ish is a rough estimate and the final, but we'll see how that goes. Cool. So there's opportunity for extra credit. Check out the symposium. I think if you're interested in this stuff at all, the symposium will be super cool. We have a wide range of, we have a professor from academia that's going to talk to us, who's a professor from the University of Texas at Dallas. She does really cool research. We have a head of the security team at Samsung Research who also has a PhD, talking about the challenges that they face. So we have some things in there. And then we'll have Perry Adams is going to give a talk. She is an RPI alum who works with DARPA and does really cool stuff. So she's going to give us a really interesting talk. About from the industry perspective. So we have kind of 3 cool views here, and then followed at the end by lightning talks, like 10-minute research talks. So, come write a report, get some extra credit. But if I don't know, stay for all the talks. It's a cool opportunity to see what these interesting people have to say. And assignment 3 will be graded by tomorrow. I'll probably end up talking about it at the start of maybe the start of the class there, or maybe I'll wait and do the whole recap on Monday. So that should be fun. Yeah, and you'll get your basically the way I like to do it is to just email you each individually your grades. So you'll get an email with exactly what we have for your scores of for all the assignments in the midterm. And of course, at this point, every single grade you have in this class except for assignment 3. So, all right, cool. And I think people are asking in chat if we can crank out 4 more assignments in 5 weeks. So who knows? Anything is possible, especially if people are clamoring and asking for it. I know. I'm sorry. It's so fun to mess with y'all sometimes. But you're good sports about it, so it's okay. Right? Cool. Okay. Now we're going to, so we we looked at how TCP works, right? We looked at literally the underpinnings of the internet, how data gets from one machine to the other. We started off with the TCP 3-way handshake. What are the 3 ways of the handshake? What are the flags that have to get set on each of the packets of that 3-way handshake? Thank you, Synac. Thank you. Excellent. So yeah, be sure to burn that into your brain. It is important. Okay. So then, okay, we did data exchange. We'll do shutdown because we did that very briefly. So again, TCP is a bidirectional stream. So either side can send data, and we saw that the ACKs are how that data gets acknowledged. And then finally, at the end, things can get shut down when one side tells the other, hey, I will no longer send you any more data. So here the client, by sending a packet with that fin flag set, means that it will not be sending any more data. And then the server will acknowledge it, maybe send some more data, whatever it wants. It can do anything at this point. And then finally, the server will say, okay, I'm done. I will no longer send you any data. It'll send a fin packet to, in this case, to the client. And finally, the client will acknowledge that it received that. And then at this point, basically, that 4 tuple is now gone. Poof, vanished. This connection no longer exists. Questions on shutdown? All right. Cool. So just like before, when we talked about, I want to make sure. Notability. I'm ready to go. Class notes. Good. Okay. Hello. All right. Cool. So just like before with UDP, we want to figure out what services are available on a specific port. So we, just like with UDP, we have a way of doing of port scanning. We want to try to determine which TCP services are available on a specific victim host. And just like we saw with UDP, there's a list on most Unix type machines in /etc/services that associates the service name with the port. And the really cool thing is that with TCP port scanning, seeing what's open, there's actually a number of different ways to do this. And they have different kind of trade-offs between the what, oh, is that highlight? Ooh, that's kind of cool. Huh. Did that by accidentally touching the little pad there. Anyways, I guess if I do it like this. Ooh, that's cool. So you guys can all see that, my laser pointer, right? Please say yes. Somebody in the chat. I'm going to keep doing this. Okay, thanks.
Yep.
It's like a prisoner's dilemma in here. You all want to keep, like cats, you want to watch the laser move around until somebody says yes. Cool. Okay. Back to TCP. So there's a number of different ways that we can actually try to determine when a TCP port is open. So let's look at one of the most basic ones. So let's go back to our flow here where we were establishing a connection. So if we're my machine and we want to see, in this case, if port 80 is open on Bing, what we can try to do is do exactly like we did before and send start the three-way handshake. What do we know when we've completed the three-way handshake with Bing on port 80? So we sent a SYN packet to port 80. We got back a SYN ACK packet. We sent an ACK packet. Yeah, so that port is open, right? There is a service on port 80 running on there. We went through that three-way handshake. What we didn't cover is what happens if there's no service running. Actually, maybe we did briefly touch on it. Essentially, what will happen is either B will just drop that packet and not do anything, or it will send back a reset packet, an RST. So we can use this one bit of information. What happens if I try to establish a TCP connection to the server Bing? I can do that all through here. So the simplest form, basically, uses the connect here is referring to the operating system syscall that the application calls, and to ask the operating system, hey, please connect to this. So it takes essentially an IP and port, and then we'll return either, yes, here's a socket, you can now send data on this socket, or it will return an error and say, hey, I couldn't connect to that service. So you can write a really easy program that is basically the equivalent of for int I is 0, I is less than 65535, probably 6 maybe, I plus plus, int result is equal to connect IP port. And then you say something like if result is equal to 0, usually in C, that means port open. Otherwise, we would say port closed. So I just wrote incredibly simple TCP port scanning. Oh, I guess let's actually do this slightly better. Oh, this shouldn't be port. This should be I because I'm iterating over it, and that's the iteration variable. Anyways, so we know, right? And the cool thing about port scanning is we only need one bit of information for each port. We want to know, is the service up or not, right? That's a bit the most fundamental basic building block of computing. And one of the nice things here is we don't need to be root. Connect doesn't need any root privileges to do. The disadvantage is if we look at this, so for every packet, for every port that's open, how many packets am I sending? So for every single port, for 65,000 ports, I'm going to send a SYN packet. If nothing's there, I'll get a reset back. If something is there, then I'll get a SYN ACK back, and then I will send an ACK back. So this can actually be pretty noisy. You want to see this work? I think this will happen much faster. Oh, by the way, here are the results from the previous one. This was our UDP port scan. So you can see that there was only one port open when we did this port scan, and it was port 17,500, which if you Google that, it is not db-lsp-disk, whatever that is. It's actually Dropbox. So this is Dropbox trying to sync. It's the LAN sync option of Dropbox, where basically it broadcasts a packet out on that port to every device on the network to basically say what other Dropbox clients are there. And then they can respond on that port. So if I look for the word connect, I can see it'll tell me there, aha, dash lowercase s capital T should be a connect scan. So I can use, if you don't know there's a lot of cool tricks to operating the command line effectively. One nice one is the arrow keys. So arrow up and arrow down will go through your history of commands. So you can easily go to the last command you've looked for. The other really cool thing is if you do Control R, you can search interactively back through your history. So you can search and then keep hitting Control R to go to the next one. And then when you're there, you can either hit Enter or I usually do Command E because it goes to the end of the line, Command A to go to the front, or Control, sorry, not Command, to do that. So we can see here that to do the connect scan, I need, well, I already forgot what it was. Does somebody remember what it was? I think it was -T. Connect. It's on this slide, so I can cheat there. Good. S capital T. Let's do all ports. Why not? 65535. All right. There we go. Look how much faster that was. We scanned a ton of ports. Oh, it also, so if, oh no, I don't know how to scroll because that does that. Anyways, if we went back up, it took an entire hour to do that original UDP port scan. Did somebody have their hand up? Wanted to ask a question? Okay. Cool. So we can see that on this machine, I have a number of ports up. I have port 22, which is the SSH port. And actually, let's, I said, yeah, so let's do a TCP dump on the local host. We'll run this Nmap scan again. And so we can actually see all the flags, all the TCP packets. So we can see, so the way to parse this is, can you all see my cursor when I'm, like I have my cursor over something at the bottom. Can you actually see that?
Yep.
Okay. Super weird. Why would it capture that? Because it's not, it's my cursor on the Mac. It's not on the thing. Anyways, who cares? But you can see it. That's good. So the flags here tell you where to look. So this flag is S for SYN. So we can see 127.0.0.1.4.6.9.0.8. So it's making a TCP SYN packet from localhost 127.0.0.1 port 946.908 to 127.0.0.0 port 30.80.78. And what does it send us back? It sends us back a reset packet. So that's when it's saying, hey, I don't know what you're talking about, go away. So if we want to look at port 22, will show us what it looks like when it sees something that's open. So we can look back here and we can see, aha, we got a, we sent a SYN packet. We got a SYN and a SYN, and the dot is an ACK. So that means acknowledgement. And the cool thing is we can see the sequence numbers. So in case you didn't believe me before, the initial sequence number is, wow, that's weird. I'm just going to kind of read it. 2473259454. And we get an acknowledgement back from the other side of 2437259455. So one more than before, with our own sequence number of 5747875530. And then finally, we get the ACK back, where we get an ACK packet back of where? Oh, so at this point, so it says an ACK of 1 because it TCP dump is normalizing our TCP stream, so it's starting each of them from these values. But if you dug into the, and this is a summarized version of the packets that are going on. But anyways, that's cool to see basically the difference here. So we can see that it does a SYN ACK, an ACK, and then we send a reset to basically say, nope, done with this conversation. So this is coming from our side. Cool. So I have SSH open. I have port 17500 is the TCP port on that Dropbox client. And I would guess, given the similarity of these numbers, these are also Dropbox ports, but I can't be certain about that. Cool. So here's what it would look like on something where there's a lot of ports open. But there's actually better ways of doing this port scanning. And specifically, oh, here, I want to go here. So we saw that for each of those, for every SYN packet I send a SYN packet, the other side sends a SYN ACK, I send an ACK, and then I send a reset. So it's basically 4 packets when it's open, 2 packets when it's closed. But the other difference is, the way to think about it is, remember we saw and we talked about that, well, you know, what we're actually trying to do is not talk to the server B, right? Because Bing is just an IP address. What we're trying to talk to is on port 80, this web server is actually who we're trying to talk to. So an interesting thing about doing a connect scan, when you do a full connect, the operating system tells the application, hey, somebody just completed the 3-way TCP handshake. You got a new connection, go do your thing. And so it then tries to process that connection. So it actually knows that somebody tried to connect. And we may not want that, because that application may be logging every connection that it gets, and then it just logged our IP address somewhere. So we'd like to try to avoid that if we can. So let's think about the case where this port is open. At what stage of this process does M know that B has a service listening? on port 80. Yeah, when it receives the SYN-ACK. So how can it distinguish? Remember, we said it's a binary value. So it gets a packet back, in which case does it know that the port is closed and nothing is listening? A reset. Yes, exactly. And then how does it know when it's open? A SYN-ACK. Great. So yeah, that's exactly it. So this is how we get that one bit of information. And there's no actual need. Like, I don't need to make the rest of these packets. I can just never respond. Right. Or I can send a reset packet and just say, hey, I don't know what you're talking about. And then the other side will go, that's weird. And then just eliminate it. So the packets never actually go up to the original application. And this is called TCP Syn Scanning. Leave them on read. That's pretty good. Yeah. So we're basically, another way is calling half open scanning, because you're leaving the connection in a half open state because you never completed the third part of that three-way handshake. So we send a SYN, the attacker answers with either a SYN-ACK packet in the case that it's open, or a reset packet if the port is closed. And then to be nice, we could send a reset packet instead of the final ACK, or we can send nothing. And the connection's never open. The event is never logged by the operating system because it never actually made a full connection. So I believe the command is dash capital S. Let's check the man page because I make a big deal about this. Yeah, so scan techniques. So we can see dash lowercase s dash capital S. So let's do that. And let's go over to the other terminal. Let's capture, I want to capture port 80 or port 2222. So that way we can see what happens when a port is open and what happens when a port is not open. So I run that, it should run. Cool, so let's look at this example. So here we have a case where we sent a TCP packet to port 22. We sent a SYN packet. They sent us back a SYN-ACK packet, just like they should do because we know it's open. And then at this point, we sent them a reset. And then at this point, the other side says, hey, that's weird. Because so you can think of what would be a normal, what would be a realistic case? Like something to think about is, should we log this because this is a clear port scan? It means somebody's trying to test our systems. Or is this something that could maybe happen? Yeah, what if, let's say, what if this other side, so if a packet wasn't received, so what'll happen is, we didn't talk about that because it's part of all this redundancy built into TCP. But for instance, if I send a SYN and I never get a SYN-ACK back, usually there's a timeout when I'll try again. So I'll send another SYN maybe 10 seconds later, and hopefully that one gets through if the SYN-ACK is the reason that it's dropping. Right? So it wouldn't be because of that, but maybe I send a SYN packet. Right after I send it, my machine dies. Another machine on the network, on my network, assumes that IP address. So the SYN-ACK comes back to a different machine. That machine is not expecting this packet, so it says, go away, reset. Right? So this is a case that's unlikely, but still could happen given the protocols. So this is why this isn't an event that's now, this event happening for every single port on your machine. Yeah, that's a little suspicious, right? But one port, maybe not so important. So we send that reset going like, hey, what are you talking about? And then at that point, the other side never replies to that reset. And then we can look at what happens in the case of a port that's not open. So here, port 2222, again, a SYN packet, 61843 to 2222. We send a SYN packet and they send a reset. So we can see the two different cases here. And now it's super cool. So we've been able to scan. Oh, I should have done something else first. Cool. So let's look at some difference here between these two. So this is the connect scan. Hello. I'm running my nice little connect scan. I get everything back. I then say, okay, great, that connect scan. I want to try a SYN scan. And it's telling me that I requested a scan type which requires root privileges. Why does doing a SYN scan require root privileges? What do you think? So in all these diagrams, who handles this communication, this three-way handshake and all that stuff? Yeah, who's sending those TCP packets? Our machine technically is sending it, but remember, so the way this is actually working, so we talked about there's a machine over here that's listening on port, an application that's running that's listening on port 80. Similarly, it's not our machine that's doing it, right? There's some I'm using some browser like Chrome that's running on my machine that wants to talk to Bing. Yeah, the operating system, right? So the way this works, otherwise, think about how annoying it would be for every application to write its own TCP stack and handle IP and handle fragmentation and handle window sizes of TCP, which we didn't get into. So all of this is actually handled by the operating system. So Chrome asked the operating system, this is the connect system call, where Chrome asked the operating system, hey, please make this connection to this IP address and port. And then the kernel is the one that sends out all these packets. And it says, great, I can send this out. I'll do the three-way handshake and I'll let you know when I'm done. And then the kernel manages, the operating system manages everything. So this is why when we originally ran the connect scan, we don't need to be root because the operating system does connect for us. But if you want to break this cycle, right, the operating system will not send a reset in response to a SYN-ACK. If you want to craft packets by hand, you have to basically ask for permission from the operating system. And so you need root privileges for that. So to be able to do anything fancy, you need root privileges here. And that's why this requires me to use sudo, which runs nmap as root. I think there's a good I am root joke in there, but I'll let you fill that in. Cool. So here's another example of TCP traffic, traffic dump that you can look at, that you can tell the difference between ports being open or not with this TCP Syn scanning. Cool. And there's all other types of scanning. This is, I don't have slides on this, but I do want you to show you this really quickly because it is so cool. So here is me failing to scroll. There we go. Okay, this is still running. Okay, so when I look at the Nmap SS, okay, so there's a bunch of different scans. There's a Syn Connect ACK window. I don't even know what that mamom is. There's other cool ones. There's TCP Null, TCP Fin, TCP Xmas scans. Let's do the Xmas scans. That sounds fun. S capital X. Let's see what that looks like. So starting Nmap. It's running. Let's check the progress because we actually don't care what the results are. And of course, I wasn't running TCP dump. That's fun. There we go. You see I used Control R to search through my history in reverse. Okay, cool. So a Christmas tree attack is a crazy type of scanning where you set all the flags. So it's like a Christmas tree, all the like flags are set and you just see what happens. So the really cool thing is if you look at the TCP specification, the RFC, it doesn't say, what do you do if you get a packet that has, like we talked about, right? What happens if you get a packet that's not a SYN packet? Do you send a reset or do you drop it or what do you do? And so these type of scans take advantage of that. And actually, I'm going to just do that. So maybe we can try to get it over quicker. But yeah, all these type of scans. So a null scan says, what if I send a packet that has no flags set, 0 flags? How the operating system handles it could depend on if there's an application available or not. And if it does, that's that one bit of information that I need, excuse me, in order to tell if the port is open or not. So if the, and the goal here, or the idea here is if this operating system implementation, I guess it's not on this side, sorry, because there's an OS over here. So if the operating system on this side varies its response to a packet, depending on if there's a service listening or not, then you can use that one bit of information to determine if the packet is open or not. It's super cool. And this idea, yeah, exactly. So that's exactly right. So the Jeremy in chat is asking about the way the operating system handles different flags isn't managed by some fancy standard. So the real root of it is that the standards do not specify every possible case of what to do if you get a weird packet, right? The standard basically says, when you get a SYN, this is how you should respond. It defines a state machine. It handles all kinds of stuff, but it doesn't say, it doesn't handle every case. Like, what happens if I get a packet with all flags set or no flags set? And if an operating system varies that behavior based on if an application is listening to that port or not, then you have a very cool, essentially almost a side channel of detecting whether that port is open or not. Let's check on our scans, shall we? Okay, I'm sure it'll say, I don't know why it has to send like 4 packets. It must be part of this scan, but I haven't done this. I don't think I've done an Xmas scan in a long time, but anyways, you can actually run this and check it on your stuff. I do see that there's a fast mode scan scan fewer ports. Okay, cool. Okay, so, and we can actually extend this idea even further. So we just said, hey, the operating system, depending on what I send, if it changes its behavior based on if a service is listening on that port or not, then I can detect if the port is listening. There's actually a more fundamental idea. So something to think about. If somebody is out there running, or I guess I have 2 systems here so I can tell. Actually, that's not a good example. So I think Windows is a better example. So Windows, right? So in this example, so my machine right here we'll say is my Mac, and so the machine here is a Windows machine or Windows server or whatever. Are those operating systems the same? Yeah, it's not a trick question. The answer is definitely no. You can even go further and ask, were they written by different people? Yes, the answer is yes. And just like we said, the specification doesn't say exactly what to do. So similar to the Christmas tree attack, what if, because the specification doesn't say what to do if I get a packet with a bunch of flags set, Now, what if Windows sends a reset when it gets that, but Mac drops the packet? What can I use that one bit of information to do? Yeah, determine what operating system is running. And why would I want to determine what operating system is running? Yeah, because that can tell me how to approach it, right? That's more information I can glean about the bank so that I can attack it. This is actually a common theme if you think about in like every heist movie, what do they have to figure out? They have to figure out exactly what the security system is. They have to figure out exactly what the vault is and what the lock is on the vault, right? And oftentimes in the movies, they will actually buy a copy of that so they can figure out how to break into it. It's exactly the same thing, right? The more information I know about my target system, the better I can craft my attacks for. And so there's not just that one difference, there's a ton of differences. And the cool thing is, over time, as different operating system versions are introduced, even within a single operating system like Windows, there are differences in how it responds to packets such that you can tell Windows 7 from Windows 8, from Windows 9, from Windows 10. And so it's a super useful and really cool. I really just like this idea that like differences in an implementation of a protocol allow you to fingerprint. So the idea is fingerprinting, just like your fingerprint's supposed to be unique. Was there not a Windows 9? Did I misspeak? Sorry. I haven't. Yeah. Anyways, Windows 10. Go straight to 10. Is there an 11 yet? I've been out of the Windows game for so long. Okay. I think 9 is 9 bad luck in certain cultures? Is that why? Yeah, I was at the I think it was the Windows 7 release party. It was very fun.
Did Steve Ballmer scream on stage at that one?
Not at that one. It was like an outdoor thing that was pretty fun. No, but he would scream at the company meeting. So we had the company meetings at the baseball stadium in Seattle. I can't remember exactly what it's called. And that guy was, you want to talk about motivation? He was so inspiring with his energy. It was crazy. And actually, the thing that he did was when he ran up on stage, he saw a few people that had iPhones that were trying to take pictures of him. And this was when Windows had Windows Phone, and he would take it and smash their phone on the ground. And then he'd have other people bring them a replacement Windows Phone. Oh, it's crazy. Yeah, it was fun. Cool. Actually, the Zoom. Anyways, yeah, it's whatever. So, anyways, OS fingerprinting. Besides my lack of not memorizing Microsoft Windows versions, and so basically, this is exactly this. So, like, what happens if we've never communicated before, and I just send you a TCP Fin packet? Do you drop it or do you send a reset? Because that's kind of weird, because why would the specification say what to do? Because a fin packet means stop talking to me. But if we've never talked, do I acknowledge that you don't want to talk to me? Undefined flags in the TCP header are sometimes used verbatim in the reply. Weird combinations of TCP flags, selection of the TCP sequence numbers can give it away. The selection of the TCP window size, and if it sends you ICMP or IP error messages, the rate that it sends error messages, the amount of packets that it sends when it sends an ICMP message, what TCP options it uses or sets. And the crazy thing is, so we'll see active approaches where you send packets, but you can actually do this in a completely passive way. So what does passive mean here? Yeah, so it's about network, right? So was the port scanning that we were doing passive or active? Yeah, active. Why active? Yeah, we actually sent packets, right? We sent packets to try to determine if something was listening or not. Passive would be like we were doing with the TCP dump, where we're just listening, right? So this is super cool. You can fingerprint remotely what machines are you're talking to or what machines are on the internet just in a passive way by observing traffic. I mean, to me, that's like super cool. It's like, I don't know, people who can like listen to a bird call and identify exactly what kind of bird it is and the gender and all that kind of cool stuff. So this can happen exactly, on the network. And there's a tool you can check out called POF that can actually do this. And we can do this actively with Nmap. So, oh, cool. So here the Xmas scan was able to tell that port 22 was open. Yeah, so here we can see the difference of the Xmas scan. So when it sent packets, now because of the way this operating system works, when it sent the Xmas packet to port 22, it never got a response. So it actually doesn't know, is somebody dropping this packet like a firewall, or is it actually open? But it does know that the other ones were closed. So it knows that in the case of this FPU on port 2222, it got a reset packet. The FPU is just the flags that are set. So Xmas must be, actually, I don't even know what F stands for. I think P is maybe the urgent pointer. I mean, I don't know. I'd have to look at exactly what these packets are, but this is just the format of an Xmas scan. And if we look at Nmap and you say, I want to do, oh, F is definitely probably fin. Yeah, thank you. So the fin and then the pointer and urgent maybe. There we go. OS detection. Cool. So we can do -O to guess the operating system. So I actually really do like doing this. We can do this -O. And there it's going to send. Yeah, so here it sent a bunch of, and it actually is port scanning as well. I guess I didn't ask it to, but it did it anyways. Oh, and let's look at all the flags that it sends. So it's just listening on the local host. Cool. So we can just see it sending a bunch of packets. You can see some super weird flags in here that we never talked about. SEW, so a SYN, I don't know even what it is, or W, window maybe. None, no flags. So you can see it's testing the system as in terms of what does it do on each of these things. And now you can see we're getting very weird, is that DNS traffic on there? That's weird. That's cool to just show up in my traffic. But so we can see that, okay, what did it learn? It learned that it's running Linux version 2.6.x, and it can basically figure that out just all through those network packets. So if you run this against one of your Windows hosts, you'll be able to see that. Unfortunately, thinking about it, I don't have any other devices that I have permission to mess with, so we won't do that. But you can kind of see how it does it, able to detect the operating system, which is just super, super cool. Cool. So now that we touched on port scanning, fingerprinting, now we can go back and revisit our old friend of spoofing and hijacking. So what was the difference between spoofing and hijacking? Yeah, so good, Eric, in the chat. So spoofing is like impersonating. So I want to make a TCP connection to one thing with pretending to be a different IP address, right? So how's that different from hijacking? not quite. So if we think about the UDP example, UDP spoofing was when I tried to send a command to a trusted system pretending to be a different IP address. And hijacking in this case was I was actually hijacking the reply. So in TCP, spoofing will be, I'm going to try to make a TCP connection to a remote system pretending to be a different IP address. Whereas hijacking is I actually want to inject data in the middle of a communication between two machines. Cool. And just like we talked about, impersonating a host when establishing a TCP connection, oftentimes there'll be IP addresses, so IP address limitations. So for instance, actually, I can give a real example from when we were setting up the midterm CTF. If you noticed for about a day, the practice CTF was down while we were setting up the midterm CTF. How I did that was I went into, we run it on Amazon. I went into their settings and I changed it so that only Tiffany and I's IP address could make connections to the website. And Amazon would drop any packets from anybody else. But if you could host a TCP spoofing attack, you could then trick the website into being you, and you could have got a day extra accessing the website. Why was I not worried about that? I didn't teach you yet. Yeah, I have such little faith. It's not that you didn't know the address of the server. You know the address of the server because you're accessing it. You don't know my address. So part of it is a little bit of security through obscurity in that you don't know my personal IP address. So it's really difficult to spoof that. We'll look at the other reason later. There's details in here, but this was the super cool thing is this weakness of TCP was known back in 1985 in this paper. If you want to check it out, you can read about this potential. Okay, so just like before, so we have some trust where one system trusts another system. And let's, Christian, are you paying attention? Can we use you again as a, all right. Well, one of you Matts can take the class next semester or the semester after that, and you can opt to be the bad person. I'm happy to, I'll even, fail you if you'd like, or EU if you like. Okay. So let's set it up like this. I actually like that we have a real example. Cool. So we have my machine, this is Adam's machine. We have the midterm server. So just like before, we'll go IPA, IPM. We'll talk about port 80 because we're talking about the and then we have Christian who's trying to get a start on his midterm. So Christian knows that the website is set up so that only people coming from IPA can actually access it. Right? Everyone get the situation? Cool. All right. So what's the packet that Christian's trying to send? So we know the IP level, the IP stuff is easy. The source, wait, is it easy? What's the source going to be of this packet that Christian's going to try to make? Yeah, so the source is IPA and the destination is IPM, thank you. And then at the TCP level, so we have the source port is, it doesn't matter, we'll do 2222. The destination port is going to be port 80. And let's see. So what other things do we have to set? So we have to set a sequence number. So Christian will say 99 for his sequence number. And what flags need to get set? Syn, thank you. Does Christian include any data in this packet? Yeah, why not? Right, because you're just establishing the connection. You literally have to complete the three-way handshake. The other side will tell you to go away if you try to send data. So great. So this packet gets sent out by Christian. It goes to M. What does M respond with? So let's first ask, will M respond? Yes, going to respond. There is a web server listening. It's not, it'll be, I don't remember what we're running, Nginx or something. There's some application running on the midterm server that's listening on port 80. So it will okay, so what are the IP addresses here? So what's the source IP of this packet? IPM, thank you. And the destination is IPC. Yeah, it's incorrect. You're supposed to let me know when I make mistakes. Thank you. You've heard that story about the professor who, oh, I did it again, actually, not on purpose that time. Have you heard the story about the professor who told his class at the start, every lecture, there's going to be one mistake that I'm going to do in class? And so that you'll have to figure it out which part of the proof that I messed up. Have you heard this story? So anyways, the class basically, copies all the notes, and every day after class, the class like gets together to go through it. And, after every class, they're spotting every mistake. It's great. And then at the end, the very last lecture, he gives the lecture and they meet and they can't find any mistake. They're like racking their brain, going crazy to try to find this mistake. And finally, at the end, they talk to the professor and they're like, we don't understand like why, like there's no mistake in here. We literally can't find it in this lecture. He's like, oh, well, the mistake from the first lecture was that there would be one mistake in every class. And then, but it got them to pay attention to the whole class. So anyways, that's what I always think of when I make a mistake, is I say, oh, I'm just testing you to see if you can tell. All right, back to at the TCP level, what's the source port? $80, thank you. And the destination port, 2222. Great. What's the sequence number going to be? Yeah, it can be anything, right? Specifically, it does not have to be 100. So that's the first thing to realize. Why can it be 1? Yeah, because it's important to remember this is now the midterm machines sequence number. Great. Okay. So yeah, so you guys already got the acknowledgement number is 100. So it's the sequence number plus 1. Okay, and the flags, what flags? This is the thing you got to get. Synac, thank you. Okay, so M sends this packet out. Where does it go? To A. What does A do when it gets that packet? Yeah, so remember, this packet comes from Christian. This packet comes from M. And now A will say, it'll say the TCP equivalent of who dis. I wonder if it keeps the source port. Anyways, let's assume that it does. That's kind of interesting. I guess it would just put, yeah, because the other side needs to know, but it's kind of weird that it does this if it doesn't know anything. And I don't think it sends anything else. And it says, go away. I have no idea who you are. Reset. And then when A sends this packet out, it goes to M. And then what does M do when it receives this? It says, okay, the other side doesn't want to talk to me. Great, I'm going to terminate this connection. So M got to the second phase of the three-way handshake, and then the connection never occurred because M never received what? What is M listening for? An ACK, that final third ACK from A. So at this point, Christian is sad because his attack didn't work. Yeah, cool. So can Christian just be sad? So yeah, at this point, now what happens if Christian sends the ACK back? So I'll just say IP the same, TCP what happens if Christian sends M this ACK packet? Yeah, the other machine, M, will get that and send a reset back because it's saying, what are you talking about? We haven't talked, right? I have established no connection with you, and now you're sending me the third part of the three-way handshake because the handshake terminates as soon as M receives this reset packet. Okay. So I guess I don't know anything about our real life Christian, but our virtual Christian here is smart. And so Christian says, aha, the solution is I need to make sure that Adam's machine doesn't send that reset packet. How can Christian make sure that my machine doesn't send that reset packet? Yeah, what if Christian DOSes my machine? So now what's going to happen is Christian will do two things. So Christian will send out packet A on the internet. And at the same time, will DOS Adam my machine such that it cannot respond to any packets. Cool. So then M sends back this syn ACK packet. It goes here. But now this ACK pack, this reset packet never comes out. It never gets sent. So Christian can start to create the ACK packet, right? So again, we're spoofing the IP address of A. The destination is the IP address of M. The source port, Christian came up with, so he knows it, 2222. The destination port is port 80. What was Christian's sequence number? So Christian's original sequence number was 99, but we know the ACK will always add 1 to it, so we can do 100. Now, what does Christian put for the acknowledgement number? Two? What's 2? And what flags does he set? ACK. Yeah, but we have a problem here. So, does Christian know the IP address of A? Yep. Does Christian know the IP address of M? Yes. Does Christian know the source port is 2222? Yep, because Christian created that. Does Christian know the destination port of 80? Yep. Did Christian get the sequence number? Yes, because Christian created the original sequence number, which was 99. So he knows that the sequence number will be 99 plus 1. But we have a fundamental problem where how did Christian know that number? And if we look at this diagram, how can Christian know that number? Right? That packet was sent from M to A. And how many possibilities are there? What was the size of this acknowledgement? So this is the key right here, is the acknowledgement number. What was the size? So I'm going to go back to the slides and tell us. A big number. How big? There's different big sizes. Yeah, 2 to the 32. So it's a 32-bit number. Right? So what's that? Roughly 2.4 billion? Or 4. Yeah, sorry. You're right. 4.2. What's a couple 2 billion between friends? Is it actually billion? Is that right? Yeah, okay, thanks. Cool. Yeah, so Christian has a 1 in 4.2 billion chance to get this correct. And what happens if Christian gets it incorrect? So what happens if Christian is only off by 1 and guesses that the acknowledgement number is 3? Reset, go away, try again, Christian. Right? Because not only is M waiting for that ACK packet, but that ACK packet has to have the right acknowledgement number. Because, and this is a fundamental part of the robustness of the network, if we're sending a packet that somehow, like, what if the 3 Christian actually knows it's 2, but a bit gets flipped in Christian's packet for some reason and it becomes 3, right? We don't want to have that conversation. So, okay. So what can we do? What can we do? You're now hackers, figure it out. Yeah, Snoops. We fundamentally, we need to do 2 things, right? We need to do one of 2 things, let's say. There's 2 ways to break this. What does saying that Christian has a 1 in 4.2 billion chance implicitly mean about this chosen acknowledgement number? Now we know there is a value somewhere. It's random, yes. Right? And that it's chosen sufficiently at random from 0 to 4.2 billion. Right? And what if it's not? What if we can guess it? What if we can cut it down so we can guess it to within 16? So we try this 16 times and we get right once. It's pretty good. Would you take 1 in 16 odds over 1 in 4.2 billion? Yeah, for sure you would take that. Awesome. Cool. Okay, so that's one way, is we can guess it, right? If it is truly random, then we cannot guess it and we're out of luck. So we need to do what people were just talking about. We need to somehow get a copy of this packet. This packet has the information that we need. So what are ways that we learned that we can snoop on other people's traffic? Yeah, how do we get their traffic to look at it in the first place? Yeah, what if we're on the same local network? So now if I take Christian out from here and I say now Christian is on the same local network as M, could Christian get access to that packet? Yeah, what if Christian's so good that he's able to get in my network. Would that also work? Yeah, that would also work. Right. And again, like we said, Christian doesn't have to be physically connected to my network. He can, if he takes over my phone, he's now part of my network. If he takes over my smart fridge, he's now part of my network. Cool. What else? Are there any other places I could put Christian? Yeah, any hop in between. That's the other crazy thing, right? This packet is traversing along this whole network. So if I can take over any switch here, if Christian actually takes over this switch, then Christian can see that packet. If Christian somehow gets access to a local network in there, these are ISPs. I don't think you can guarantee necessarily, but you can make educated guesses. And if you're, let's say, if it's not Christian, if it's the NSA, if you think of a nation state level adversary who's willing to spend, I don't know, a couple $1 million on this, they could probably make that happen and figure out which route it's going to take. It is not hard to search for one packet going through those routes among billions. The switches do it, they can do it, and we can make hardware that can do it. And if we're on the route, we actually have an easier job. We don't even have to DOS my machine. We can just steal that packet, never forward it, and do the response. So the good news is, in terms of security, this is fundamentally similar to UDP in that UDP spoofing, or it's different from UDP, right? There's a built-in security mechanism here in that as long as that acknowledgement number sent by the server is random and unguessable, then it becomes very difficult to break TCP. But if we're able to do that, then we know how to do it. Cool, that was fun. So yeah, send a SYN packet to spoof it, reply with a SYN-ACK, and then try to guess it. So we need to reply with an acknowledgement of that sequence number +1. So we can either eavesdrop it or guess it. So this is exactly the same scenario that we talked about. How are we doing on time? Okay, cool. So similarly, Christian here. Actually, I'm going to do a new diagram. So I'm here. And here's the midterm server. And what Christian wants to do is I'm actually accessing the midterm server, and he wants to inject in my connection the fact that basically a command that says set Christian's grade to be 100 on the midterm. Or how about you want to really hack it, Christian, and give yourself 200 out of 100? You're going to settle for 110? Man, all right, fine. All right. All right, so okay, cool. So what's happening is we already have a connection here. So I'm going to stop drawing the IPs, source port. Again, we'll use 2222, D port 80, sequence number 99, flags SYN. So A sends that to M to start the connection. What are you all doing here? Go away. I need the space. And then M responds with a syn ACK. Sequence number 1. I'm going to use the same ones as before. Acknowledgement number 100. Source port 80. D port 2222. So this is the second packet that gets sent. I guess I can number them. I don't know if that helps, but okay. So the syn ACK. Now, okay, 80, sequence number is now 100. We're acknowledging that we've seen 2. The ACK flag is set. Now this packet gets sent, packet number 3. Cool, 3-way handshake, everything good. So now, as time goes on, each side will send each other data, and now Christian would like to interject and send a packet as if it's coming from A. Oh, yeah. So the TCP, and I'll just do the IP here because I think it's could be useful. Okay, so Christian's going to spoof a packet with the source of IP of A, destination of IPM. And then at the TCP level, Christian is going to say that the source port is 2222, D port is 80. Now we have a problem. Again, similarly, we said some data has been exchanged, so we don't actually know what the sequence number and acknowledgement numbers is. Let's say that Christian is able to know that because Christian is somewhere along the path. So we can say Christian knows, well, the sequence number is 150. So basically the last, so this way's sequence number is 150 and this way's is 10. So acknowledgement number 10, flags ACK. And now Christian wants to inject some data. Set. Do you have a cool hacker handle, Christian, on the website? Actually, it's okay. Don't write it in chat. I don't want people to. Set Christian grade 200 because he's very bold. All right. Does anybody know how many characters that is? I guess I'll count it. 1, 2. So 23 characters, including the new line at the end. Okay, cool. So Christian sends that packet out. Now, this has the proper, again, we still have the problem of getting these sequence and acknowledgement numbers, but let's say that it's okay. So Christian gets that packet, injects it here. M will receive it. How will M reply to that packet? Yeah, it'll acknowledge it. So it'll say, great, source is IPM. Destination is IP of A. Source port is 80 in this case. Destination port is 2222. Now the sequence number for M is still 10. M has not sent any more data. The acknowledgement number. So now what is this going to acknowledge? What's the acknowledgement number going to be for M? So it's going to be 150 plus the size of the data that we've seen. Yeah, 173. Thank you. And the flags are going to be ACK. Cool. So M sends this to A. What does A do when it receives this packet? So it's 73 because the last sequence number from M is 150 and we sent 23 bytes. So it's not going to say reset. What it's going to say is it's going to send a packet back acknowledging how much it's sent so far. So it'll say, hey, that's weird. I'm IPA. I've sent a destination of IPM. Port 2222, D port 80. My sequence number that I last sent you was 150. And I will acknowledge up to 10. So A will send this back to M, and N will say, excuse me, sir, I think it'll actually send this packet again and say, actually, I've received, and I'm acknowledging that I've received up to 175. And A will get that back and say, I have sent you up to 150. And this will actually, well, okay, I think I lied. Shoot, I need to make it slightly more complicated. So what M will say is, no, that's not right either. Okay, cool. We can keep it like this. I think this is fine. Okay. So essentially they're in a fight now because they don't know. They've gotten desynced. If you remember back to that thing I just deleted of the stream where the sender thinks we're at 150, but the receiver thinks we're at 173. And every time the sender sends a sequence number of what it's sent so far of 150, and every time it gets that, the receiver will acknowledge saying, hey, I've seen up to 173. And the sender says, I've sent up to 170 or 150. And they actually just keep sending that back and forth until a packet gets dropped. It's called actually an ACK storm because a bunch of ACK flags get sent. No, it doesn't do +1. The +1, sorry, for the acknowledgement number, the +1 only happens on the very first packet. So the sequence number you can think about is what byte you're expecting next. So the 23 bytes go there, and then you're expecting 173. Cool. So you can, yeah, with this technique, you can inject data into a stream. So think about if you were able to get into my TCP, my SSH section, right? You were able to inject a command. Or if on the midterm website, you were able to inject into somebody's connection to the server, you could inject when they're using the terminal rm-rf star to delete all their stuff and mess with them. Again, sequence acknowledgement numbers must be correct. So we have to either eavesdrop or guess. This is described here. And the other thing is you want to wait till the connection is quiet when there's not a lot of data transferred. But the problem is that desynchronizes the connection, which is what we just looked at. So let's, cool. So anyways, they keep retransmitting this until we do this. So anyways, we can see this, we spoof this TCP packet. It acknowledges, and it keeps going back and forth of this acknowledgement. You can actually, let's see, I don't have the TCP traffic. All right, I guess I cut it for time, which is good because we're running out of time. So anyways, but the cool thing is if Christian actually sits in the middle of this connection, so if Christian's vantage point is in the middle, and Christian can control that traffic, he can actually change up and fix the sequence and acknowledgement numbers so that both sides think that they each know what the other sequence of acknowledgement numbers, but actually Christian is making up for that 23 byte difference. Oh, thank you, Watch. I wasn't talking to you. Cool. Anyways, yeah, I think that's class, right? Have we been going? Yeah, 6. Okay. Thanks, everyone. I appreciate it.